Thank you. And so, good morning, everybody. So, I'm going to start this third lecture on quantum fluids of light. And so, as I promised in my outline, so today we are going to talk really about polaritons in lattices and how we can use them to emulate different kinds of Hamiltonian, and in particular, how we can enter the field of topology. So the way I'm going to explain these experiments, so I've chosen three experiments, and actually this is somehow chronological. So the first experiment is actually an experiment on quasi-crystals. So we were first interested in emulating a quasi-crystal, and thanks to cavity polaritons, being able to image the modes in real space, in reciprocal space, and we were working with Eric Ackermann, who was interested to evidence some log periodic oscillation in the spectrum. And then we realized that actually quasi-crystals have also topological properties, and so we decided to try to measure topological invariants using our system. So this is the first experiment I will show you. Then we really entered into the field of topology, and we wanted to implement the simplest system as possible, which is a bit like a toy model for topology, which is the 1D SSH chain. So I will explain how this works. And we, using the non-linearity and the gain that we have in our Polariton system, we could actually trigger lasing on the topological state and show that this lasing mode has some protection, so robustness, which is related to the topological origin of the mode of the laser. And then we will move to more complex systems, so the 2D honeycomb lattice, which is much more interesting for topological properties. So I will show you where we are. So for the moment, we can image Dirac cones, we can image edge states, we can look at the S-band, but also at higher orbital bands, which are also very interesting. And then at the end, I will show you our perspective to really fabricate a topological photonic insulator, so what we need for that, and so where we are. And at the end, I will try to show you, to explain you what are the perspectives for the field. Okay, so first, some very general remarks about topology. So in mathematics, if you consider surfaces and the properties of surfaces, there are properties which are sensitive to local detail of the surface. So like, for example, the curvature of the surface. So it can be very different depending on the position where you look at it. So this is really a local property, and this is very sensitive to deformation. And then there are more general properties, which is, for example, the genus number, which is the integral over the surface of this curvature. And this property is really a global property of the surface and does not change if you perturb, if you deform your surface. So this is a topological invariant. You have actually different classes of surfaces depending on their genus number. There is no way you can transform one surface into a surface which has a different genus number just by deformation. So for example, you can understand this as this. So for example, here, this is an orange, and you see that you can show that the genus number is equal to 0, and you can transform this into a pineapple or into a plate or into whatever. The genus number will always be 0. Here, this donut has a hole inside, and this corresponds to a genus number equal to 1. And you can transform it. I had before a picture of a cap, it has disappeared. So you can transform it in anything you want, but if you don't deal another hole, it will always remain a surface within this general ensemble. Okay, so these are properties which are very robust and do not depend on the really precise detail of your surface. So in physics, we have also this kind of different quantities. So there are physical quantities like energy dispersion, wave functions, which are very sensitive to local perturbations. So if you take a lattice, you can engineer the shape of the band structure. If you introduce defect, you can have defect states in your gap. So you can have all kinds of structure, and so the band structure is really sensitive to local properties. And then there are also global properties, so which are quantities which are integrated over the band structure. So like these now very well-known Chern numbers. And these Chern numbers, they are very distinct properties of the bulk, and they don't depend on exactly the precise shape of your material. So these Chern numbers are insensitive to local perturbation, and this is why if you have topological edge states, they will not be sensitive to defects or to any kind of disorder. They will just go straight because they have this topological protection. So one of the nicest experiments, which is known for a very long time, but which has been revisited in terms of topology, is the integer quantum Hall effect. So actually you can describe it, I will come back to that, with a lattice and show that you have bands which are the Landau level, which correspond to different Chern numbers. And so the conductance, so when you measure the conductance of your sample, you have actually plateau, and these plateaux are universal. They only depend on very fundamental constants and the Chern number. So the conductance is equal to E squared over H times this integer, which is the Chern number. And whatever the semiconductor you use, whatever the sample, if there are defects or whatever, they are grown in Japan or in France or wherever, they will all show the same resistance, and this is of course very interesting for metrology. So this kind of topological properties actually arise in a spectacular way when you want to make an interface between two materials which have different properties. So for example, when you want to make an interface between a band which has a Chern number equal to 1 and a band which, and the vacuum, for example, which has a Chern number equal to 0. So then there is no way you can connect these two materials without closing the gap and reopening eventually the gap in another material. And closing the gap, the only way to do that is to introduce an edge state. So these edge states, they exist because of the topology, and they will always be there if you want really to make a boundary between two states. And so here you see that the edge state traverses the gap as you sweep K. Okay? And so these edge states are responsible for the conductance in the quantum Hall effect. So you can also imagine them as cyclotron orbital, which reflect at the edge. This was the way people understood quantum Hall effect at the beginning, but there is a much more general way of thinking about that, considering topology. So the field of, trying to get topological material started to interest also people working in photonics, and we saw very nicely in German talk of yesterday afternoon. There are very, very beautiful experiments which were reported lately, trying to implement, so to try to generate topological 2D material and see the propagation of light through the edges. So one of the most beautiful work is this one. So in this paper, this is done in the microwave regime. So they use magnetic material which break time reversal symmetry, and they were able to observe chiral states, so propagation of light in one direction, and you see here there is a wall, and the light is just going around the wall without any possible backscattering. So this is in the microwave wavelengths. Here these are works done in the optical domain, so either using coupled waveguides or coupled micro ring resonators. And these experiments are done with dielectric materials, so non-linearity. So our goal was to try to go into this field and try to see first if we can reproduce such an experiment, so building really a topological insulator for optical light in the optical domain, and then try to see if non-linearity can bring something into the physics. The field of topology with even just weak non-linearity, so Kerr non-linearity, is quite open. It has not been explored very much. So this is what we have done. So the outline of my talk will be the following. So I will first describe you this quasi-crystals, so this quasi-periodic structure we have done in a 1D wire, and how then we could try to see edge states and measure their topological invariance. Then we will move to this SSH chain. So this is a 1D zigzag chain of coupled micropillar. And at the end of the chain, we could visualize an edge state and have it laced. So we will see that in detail. And then we will move toward 2D lattices and see how we can go. So quasicrystals, so just a very general introduction. So this, you know that in the solid states, you have amorphous materials, which are completely disordered and have absolutely no long-range order. We have crystals, which are periodic, which has translational in symmetry, and have obeyed to the Bloch theorem and to this kind of half band structure, which are governed by their symmetry. And then you have this kind of intermediate materials, which are quasi-periodic, which have no translation symmetry, but some long-range order. So they have some intermediate property. And so they were discovered experimentally in 1984, where people did some X-ray diffraction on aluminum manganese alloy and observed five-fold symmetry, so which is forbidden in periodic crystal. But you see here that indeed you see that there is a five-fold symmetry, which is the signature of a different kind of order for solid state. And the same year, actually, a mathematician proposed the idea of having this quasi-crystal in some Penrose tiling arrangement. So what we have implemented is a quasi-crystal, which you get when building a Fibonacci sequence, which is very famous in mathematics. So what we want is to build for Polariton a potential which obeys this Fibonacci sequence. So so there are many ways of generating a Fibonacci sequence. There is a way which is called the substitution method, where you consider two letters A and B, and then you build words, and you pile these words, and at the end, the sequence of AP letters obey to the Fibonacci sequence. There is a geometric method where you start from a square lattice, and you project the points of this square lattice onto a straight line, which has a slope, which is the golden mean. So you take like a rub between on each side of this straight line, and you project all the lattice points which are within this rub onto the line. And this also gives you, so you get a series of points, and you can show that there are just two distances between adjacent points, and the sequence of distances obey also the Fibonacci sequence. So here we are going to use a different method, which has been actually proposed quite recently by Israeli young and very brilliant scientists. I will talk about them later again. And so they proposed this way of generating a Fibonacci sequence. So here you take the sign of this formula. Here sigma is the golden mean. J is the number of the sites you will consider. So you consider that you want to put n sites from j equal 1 to j equal n. And for each site, you calculate this number. And phi is a phase that you can choose as you want, which is called the phasor. Okay? And so you will get a number, either +1 or -1 for each site. And this sequence of +1 and -1 will obey the Fibonacci sequence. Okay, and so what we want to do is to convert the +1 into a value of a potential, and the -1 in a different value. You see, so for example, this is +1, this is -1, and we are going to construct a potential which follow the Fibonacci sequence that we got from this transformation. Don't hesitate to interrupt. Sorry? So the golden ratio tells you that there is no periodicity. This is an irrational number, and it assures you that there is no way you will get a periodic, it will be aperiodic. If you take an integer, then you will get a periodic structure. The Fibonacci sequence is this sequence of +1, -1, +1. So here you see you have +1, -1, +1, -1, +1, +1, -1, and so on. And this is the Fibonacci sequence. I cannot demonstrate you why you get the Fibonacci sequence. This is the question. What is the question? You understand? Okay. Exactly. So the substitution method that you can take is that you take two letters, A and B. So you build, so this is going, so then you, so the first sequence for with one letter is going to be 1. Then S2, you take it by attaching the first word with the, no, this is the first letter, this is the second letter, and then what you do is you attach the last word to the previous one. Okay, so this is A, this is going to give you BA. Then the next one is going to, you attach this one, BA to the previous one. Okay, and so on. So you have N, Sn plus 1 is the word that you get attaching Sn to Sn minus 1. This is going to give you a sequence of letters which has the same mathematical properties as what you just said. Okay. And so they found a way here to write another method to generate this Fibonacci sequence, and the purpose is to introduce this phi. Because then with this phi, you can map it to the quantum Hall effect. So the way you construct this sequence is that the third one is you attach the letters. You build a word by attaching to, the n plus 1 sequence will be the sequence n attached to sequence n minus 1. No, I agree, but you can show that you get the same. So this is called the substitution method. There is another way to generate the Fibonacci sequence. I'm going to show you that. Oops. So I'm very bad at drawing on the blackboard. I need a few points, otherwise I will not manage. So what you do is you take a slope which has a line which has a slope which is the golden mean, and you take two parallel lines, and you project onto this line all the points which are between the two lines. And what you can show is that there are only two values of the distance between two adjacent points, which are, we call A and B. And then the sequence of A, B, so you see here, this is B. Well, my drawing is not correct, but you get a sequence of A, B, and so on. And this is also a Fibonacci sequence. And then when you do that, phi corresponds to the position of this line. Actually, you can, when you change phi, you move this line. And so if you want to consider a Fibonacci sequence with only n letters, you can show that, so phi is an angle, and you can show that the sequence are phi period, are 2p. I mean, if you sweep phi, you will get, so you will see that when you sweep this curve vertically, some points will go out from this region I'm considering, and some points will go in. So you will sweep B into A and switch B into A and A into B. Okay, so you will get different sequences. So if I have n letters, I have n possible sequences, and I will get them when so phi is 2 pi. I mean, going to the sequence is 2 pi periodic in phi. So when you change phi, you will switch A into B and B into A, and so get a certain number of sequence. And after having swept phi by 2 pi, you will recover the initial one. Okay? More than that, I'm not able to see. And so these people, these Israeli people, were studying a different kind of quasi-crystal that I will show you, where you can also generate it using this phazon. And what they showed is that the expression they have is exactly the same as the quantum Hall effect that you can describe in a square lattice. And so they could, yes? I will come back to that later, okay? You want to say phi is what, you can choose it. It's an experimental theory. So this paper, what I will show these people, they are a very clever theoretician, but all their paper is associated with the theory, with an experiment with coupled waveguide. Okay? So, I'm happy to have questions. Okay. So, the idea is that we want to create this sequence of B, A, B, blah, 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 and try and convert this into a potential for our Polaritons. So what we do is we take a one-dimensional wire, as I described several times during the lecture, and we are going to introduce a perturbation to this 1D dispersion by modulating the width, the section, the transverse dimension of the wire, following this AB and so on. Okay? So this is A, for example, corresponds to a wider region of the wire, so a lower potential, and B corresponds to a narrower region of the potential, so of the wire, so a higher value of the potential. Okay, and so we construct wires one after the other, corresponding to different values of the potential of the letters to just investigate it. So here you see typically the size of the letter is 0.8 micron. And the two widths corresponding to the two values of the potential are this one. Okay? So we choose a number of letters. I think here in this experiment there was 233 letters. So 233 values of AB. So what do we expect for this kind of structure? So if we go back to the periodic potential, we know that if we apply a periodic modulation to a free particle dispersion, we will open gaps at values of k, which are a multiple of pi over A being the period of the potential, and we will open gaps which are proportional to the amplitude of this perturbation. And what we also know from the Bloch theorem is that the number of states in each band are the same. So it means that the density of state, the integrated density of state, will present steps equally spaced. These are the different gaps, and in each gap you have a constant. These are the gaps. In each band you have the same number of states, so the height of these steps are the same. So it has been shown that for a Fibonacci potential, you have the analogous of this Bloch theorem, but which is a bit more complicated. You may open gap for any value of k, which obeys this relation. So sigma again is the golden mean, and p and q are integer. Okay, and the density. So this work has been this kind of labeling of the gaps has been called the gap labeling theorem and has been explained very nicely in this paper. which is very difficult for physicists like me, experimentalists, but it's a nice paper from Jean Bélissard in 92. And so what he showed is that the density of states also presents steps, but this time they are not equally spaced and they don't have the same height. Okay. So we did the experiment and see how the dispersion looks. Yes. So, I mean, depending, so what we want, I mean, the gaps are going to be related to the amplitude of the wire. And so what we try to do is, so what the main problem from the technological point of view is the narrow part. If it's too narrow, we will induce non-radiative recombination and it will be a mess. So 1.86 or 1.9 micron is already very small. And so this is very wide, this is very small. So that's somehow the largest amplitude we can do. And then A, so what you know is that the value of the gaps are going to be related to pi divided by A. So if we take A very large, then it means that pi over A is going to be very small, and all the gaps are going to be in a tiny region, and we will not be able to see anything because things will not be resolved. So we choose a value, again, not too small to be able to, because if it's really, really too small, Polaritons are going to average everything and we will not see anything. So 0.8 is an intermediate value, which is not too small, so Polaritons fill the detail of the potential, but not too large so that we can resolve as many gaps as possible. So this is the kind of trade-off we had to do to design the sound.
Okay. So you fabricated many different samples with different phase.
So this is what I'm going to explain afterward. We are going to sweep phi. So we are going to look at a set of wires with all n possible values of phi so that we see all the switches. And we are going to monitor the edge states in this structure. This is what we are going to do. At that time, we were using the substitution method, and phi is actually hidden. We did not care about phi. Okay, so this is what we observe. So this is the experiment. These are the calculations done in the group of Eric Ackermann. So you see that we have actually a quite complicated band structure. We have 3 bands and 2 gaps. And then you see that inside these bands, we have additional gaps. So what we did in this experiment is actually label all the gaps. So we were able to find these 2 integers and see indeed that we could use this gap labeling to really see where these gaps are. Okay, so what is really nice is when you look at the modes in real space. So now we make an image as a function of the energy of the Fibonacci, the mode, the Polariton modes in our structure. So this is the experiment. This is the theory. So I don't know if the contrast is good enough, but actually there are really many little details in the theory that actually are reproduced in the experiment. So when you see the weird things actually in the experiment, these are reproduced by the theory. So these are really an emulator where you see very complex modes which present actually. So one thing that would be interesting is to look at the localization of this mode. They should present critical localization with power law decay. So yes. No. So here I'm just pumping non-resonantly and putting Polaritons everywhere. So Polaritons, actually, I don't need Polaritons. I could put a broad distribution of quantum dots. I just need some light inside which shines from inside and so that I can see the modes. So for the moment, there is no really non-linearity or anything there that is interesting with Polaritons. This is the next step. We have not gone through that, but doing some nonlinear physics inside such a weird spectrum may be very interesting. So from this, so here what I show is the integrated intensity, for example, integrated in real space as a function of energy. So I integrate this kind of image along the x direction to get just the signal as a function of energy. So I get this kind of structure. So you have the 2 main gaps, and then 2 additional gaps, and so on. And then I can actually integrate this intensity to get the integrated density of state. Okay, so the population of this mode is so homogeneous that I can actually consider that the population of polariton is the same, and so that the intensity really reflects the density of state. And so what is nice is that when you compare to the theory, you see quite a good agreement, and what you see is that indeed, in the theory, you have the three main bands, two gaps, then you have inside each band again, three bands and a gap. And if you further zoom in, so in the theory it's easy, you again find three gaps and two gaps and three bands. So it means that the spectrum is fractal. So it has some self-similarity, and the more you zoom in, and you get always the same structure. So this can be nicely shown in log-log scales. If you want to zoom in, you do things in log. And so the theory shows you this log-periodic oscillation of the density of states. So this log-periodic oscillation was something that Eric Ackermann was really trying to see in an experiment. And so you see the experiment in blue. So we see some oscillation, at least 2, 3 if you are optimistic. And why don't we see more? It's just the spectral resolution of our experiment. So if we use higher Q, we may be able to reveal smaller details. So we are limited by the line width of our polarity. Okay? So a similar experiment was also done with microwave resonator, the 2D lattice, by the group of Patricia Vignolo in Nice. Just like, I mean, it was really at the same time. Okay, so now that we have this quasi-crystal, I come back to this paper from 2012 from these 5 scientists, which I think were just postdocs chatting together and deciding that they were interested in topology. So this is really amazing. And so what they were doing is actually looking at the quasi-crystal, which is different. So which is the Aubry-André quasi-crystal, which you can get in a tight bending model using this this equation. The yellow is not very good. Huh? Do you see what is written? Or maybe is it okay, or I can remove the yellow actually? So what they do is that they solve this tight bending Hamiltonian, and so here B is an irrational number to get a quasi-periodic structure, and phi again is a phase. Okay? And then what they notice is that in this very old paper from Hofstadter, there is an analysis of the integer quantum Hall effect using a lattice, a square lattice, where you consider a lattice where when you go around such a unit cell, you acquire a flux, which is in the paper named phi, but here since phi is our phazon, I named it B, which is the way it is noted here. Okay? And so what is very interesting is that you see that the two models, they are exactly the same. Okay? And so they realize that there is actually a connection between K in the 2D lattice and phi. Okay? So the same way H states, so the fact that these two models are the same are going to show you that this quasi-crystal is going to have the same kind of properties as the fractional quantum Hall effect, which means gap spectral, Chem numbers, so connected to the band structure. And so what we have in the quantum Hall effect is that there are edge states, and these edge states, they traverse the gap when you vary K. Okay? So there is a periodicity in K, so K is a periodic number, and the edge states, they traverse K when you sweep K. It traverses the gap when you sweep K over the Brillouin zone. So they had the idea that the phazon is actually a syntactic dimension for your 1D quasi-crystal, and that you should observe edge states, and these edge states, they should also traverse the gap as you sweep phi. Okay? And the periodicity should be 2 pi, exactly the same way as here. Okay, so they made the link, they made a mapping between a quasi-crystal and the quantum Hall effect. And then they also did in another paper the mapping between the Aubry-André and the Fibonacci spectrum. And so this is exactly as when you are friend with a friend, and the friend of my friend are my friends. When you are mapped to the both to the, so when one is mapped to the integer quantum Hall effect and the other one is one mapped to the first, then the Fibonacci is mapped to the topology, the integer quantum Hall effect, which means that there should be in topological invariant edge states and some key role played by the Phazon also in the Fibonacci sequence. Yes, so here this is what I show is an experiment. So this is the calculation they did. Okay, so they calculate the band structure. So you see that there are gaps, there are edge states, and they sweep phi. And you see that the edge states, they traverse the gap as you sweep phi. And this is an experiment. So this is the sketch of the experiment. They implement a chain of coupled waveguides, which follows this Aubry-André model. And they prepare the system in an edge state. And what they do is they adiabatically sweep phi along the structure. So they distort their chain so as to adiabatically sweep phi. And what they see is that the light comes out from the other edge. So actually they have completely swept these edge states over the gap. And this is the experiment. Okay? Then they did another one. So this is what they call topological pumping, when they sweep phi adiabatically. And they did another paper with the same experiment with the topological, with the Fibonacci sequence. Okay? So the only thing is that here, they just observe their edge states in real space. There are no way they can measure the band structure, look at the gaps, and so on. Okay, so this is where we come. So then, so again, talking with our friends at the Technion, what they propose to image the Fibonacci edge states is actually not to look at the edge, which is a bit more complicated, but to fabricate such a palindromic structure. So you take a Fibonacci sequence and you reverse it. And what they show is that at the edge, you see in each of the gaps, you see edge states. And these edge states, they are, so the gaps, their chain number, their winding number is related to the Q, which we found in the gap labeling. So there is actually a connection between gap labeling and these topological invariants. And so what they show is that if you sweep phi, so this is an experiment where you see the band structure. So what they do is they zoom in each of the gaps that we found in the gap labeling. So for example, this is a gap with Q equal 2, and they zoom in. So this is the gap. What they show is that when you sweep the Phazon, when you sweep phi, you have an edge state which is going to traverse the gap, and the number of traverse within the interval between 0 and pi is equal to actually Q. Okay, so for example here, we take another gap with Q equal -2. Again, we see a gap state which traverses the gap, but in the opposite direction because Q is equal to -2. Here you take a gap which is labeled by Q equal to -4, and you find 4 traverse, okay, when you sweep phi. Okay, so the idea is that measuring edge states and looking at their traverse, you can directly measure this topological quantity. So this is what we tried. What we did is implement, so etch a set of wires, so much more than 6, actually a large number. I don't exactly, I think there was about 55 structures. So where we take a Fibonacci structure, its image, and this is for a given value of phi, and then we do another one for phi 2, phi 3, and so on. So we sweep phi so that to get the end, so this 55 possible Fibonacci structure. So between each sequence, you have some A and B letters which have switched. And this is what we get. So this is one image for phi equal to 0. So you see that we have the band structure, so we have these modes. But what you see is that in the 2 first gaps, we very nicely see edge states. So there are 2, so unfortunately because of limited resolution, we can see only in the largest gap nicely these edge states. So which correspond to Q equal -1 and Q equal to +2. So you see them in reciprocal space, and you see them in real space. You see that they are localized around the interface between the two palindromic structures. Okay? And then what we did is look at this edge state on different wires corresponding to different values of phi. And what you see is that the Q equal to -1 traverse once in this direction, while the Q equal to, I'm sorry, it's Q here, equal to -2 traverse twice and in the opposite direction between 0 and pi. Okay, so we really see that we can have access to this topological invariant by sweeping, by changing phi. Okay, so it's like a synthetic dimension of this 2D lattice. So this is what the theory gives. So it's a nice experiment. And what we see also, which was not predicted, and which you can see only on these generalized edge states, which are at the middle, so between two palindromic structures that you will not see at the edge, is that actually the Chem numbers, the topological invariant, are also encoded in the symmetry of the edge state. So what you see here is that for phi in the first quadrant, so between phi 0 and pi over 2, here the two edge states so have opposite parity, you see. And what you see is that here when you go to the second interval, so between pi over 2 and pi, this Q equal -1 state has not changed symmetry, but the other one has changed symmetry. So after one traverse, when it comes back, it has switched symmetry. So here you see the symmetry. So here I take positive for a minimum, and I mean this value corresponds to a minimum, this one a maximum. And you see that the Q equal -1 switches once, whereas the other one switches twice parity. Okay, so in different systems, if the spectral information is not accessible, you may look in real space and see actually the topological, measure the topological invariant by looking at the switch in parity of your edge states. This was our first step into this topological field. So already quite complicated, and now we go to a maybe more simple system, which is this 1D SSH chain, which had been implemented in different optical systems already, but with linear medium. And here what is interesting is that we have gain in our cavity. So here polaritons are going to play a role, and we can actually base. We will see that we can base in the end of the chain. So this SSH model, which comes from Su, Schreier, Eger, so it's a paper, very old paper from 79, which goal was to describe the electronic property of polyacetylene. And so in a tight bending approach, polyacetylene can be described by a chain of sites where the coupling between adjacent sites is the periodic, has some periodicity. So you have a strong link, weak link, strong link, weak link. So this corresponds to this double bonding that you have here. Okay? So in a tight bending model, you just have two atoms. Actually, they are the same, A and B. I'm sorry, this is A. There was a mistake in these slides, which I corrected once, but I took an old version. So the only thing that you modulate, so these are the same atom, blue atoms, blue sides, but you modulate the transmission between adjacent sides. So you have T and T prime. Okay, so you have a modulation. So when you treat this tight bending Hamiltonian, so you can write it that way. So you have T and T prime, which are your two transmission coefficients. You put the energy or the on-site energy equal to 0. So the two atoms are the same. This is why we have 0 on the diagonal. And K are the wave vector of the block modes that you are going to construct. So what you get is that for T equal to T prime, there is no modulation. So you just have a parabolic band structure. But when T is different from T prime, you open a gap. And of course, whether T is superior to T prime or T is inferior to T prime doesn't matter for the bulk. It's the same. It just depends how you define your cell, whether it starts with A or whether it starts with B. Okay? So now the eigenstates can be labeled that way. So can be written that way, where phi is a phase. And you can calculate the winding number which correspond to this, the analog of the Chern number, but in 1D, which is named Zach phase. And so this is actually the integral over k of this phase. What you find, so depending on whether you define your cell that way or that way, what you find is that the winding number you get is not the same. So it's going to be 0 if you start with a strong link and 1 if you start with a weak link. Okay? And this is going to give rise to an edge state. If the edge starts with a weak link, you will have no edge state if you start with a strong link, if you make an interface between your chain and the vacuum. Okay? So by the way, this idea that you deduce the presence of edge states from the bulk properties is called bulk edge correspondence. And I was I found it very funny to discover that there is actually a new series of conferences which is called BEC. But BEC doesn't mean Bose-Einstein condensation, but means bulk edge correspondence. So be careful if you want to go to such a conference to check what you are interested in. You may be surprised. Okay, so what we did is implement this lattice. So using our micropillars, where you have discrete polariton states, so the S states, and then 2 P states, and so on. And we look at the hybridization of these orbitals within the lattice. And so what we did is actually a chain. So you could implement the SSH model by changing the distance between 2 adjacent pillars. So modulate, so making a chain with pillars which are close, then far, close, far, to modulate the coupling. Okay? But then, so what I did not say is that the width of the gap is equal to the difference between the 2 transmissions. And with such S orbitals, it's not possible to change a lot the coupling. So actually we see the opening of the gaps, but it's not as nice as what we do here. So what we do here is a zigzag chain where we don't change the distance between adjacent pillars, but we look at p orbitals. We look at px and py orbital. And what you see is that for the px orbital, for example, here there is a strong link, and here a weak link, strong link, weak link, and so on. Okay, so here for this chain, T is larger than T prime, and so you don't expect any edge states for this manifold. And for the other one, it's the opposite. For Py, you start with a weak link, then a strong link, and so on. So here, this is the topological chain, and you expect to have an edge state. Okay, so we have actually the two for the same price. We have the topological and the trivial chain, just looking at different orbitals. Okay? So when you make the calculation, indeed, you find that you expect to see a gap state. So there are 2 gap states because there is one at one end and the other one at the other end of the chain. And for the px orbital, you expect no gap states. So what is also interesting is if you look at the bands, so the modes, here we plot the square of the wave function of the states, all the states, so we sum the probability of a position on each pillar integrating over the whole band, so the bulk, in the bulk. So what you see in the trivial chain, which has no edge states, is that we have an equal probability on each pillar. These are the bulk block modes. What is interesting is that in the trivial chain, what you see is that in the bulk band, there is extremely little probability on the first and the last pillar. So the first and the last pillar have essentially only orbitals coming from the edge state. Okay? So there are 2 signatures of these topological properties of the chain. There are gap states in the gap, and there are also edge states in the gap, and no probability of the py, so no contribution of the py orbital on the first and on the last pillars. Okay? So this is what we observe. So now I come to experiments. We can so we use an elongated elliptical excitation spot that we can position really far from the edge, so just looking at the bulk. or we can position in a place where it overlaps with the end of the chain. So what you see in the bulk, so here this is the S band, which has no modulation, so it has no gap. This is the P band, so there is a really big gap. This is really because T and T prime are very different with the P orbitals. And then this is the T band. We are not going to look at that. And what you see is that when you look at the edge, what you see is two very nice lobes here at the edges. Okay, so we see, in the gap, sorry. So we see that there is something new with respect to the bulk. We see states in the gap. So things become more convincing when you look in real space. So here I show you 4 different images. Here this is an image where we look at an energy close to k equals 0 in the S band. So we see emission from all the pillars. There is nothing special. And here I show you emission, which is measured at an energy close to the lower P band. And here this is at the top of the P band, the second P band. And we see actually that the emission pattern has a 0 at the center, which is characteristic for the P band. And what is nice is that you have these edge states. And so when we look at the energy in the gap here, we see no emission from the bulk, and we have only this emission coming from the end pillar. And what is even more beautiful is that we see that we have only emission from the PY. Okay, so this is really the topological chain and the PY state. And what you can see also is that if you look at the bulk of the P band at the end pillar, you see that there is no orientation along PY. We clearly see that it's PX only, which is exactly what I've said before. The bulk modes are evanescent on the first pillar. Okay? So this is really a signature of this topological property. So then what we did is to position our long spot overlapping the end pillar and see what was going on when we increased the non-resonant pumping. And we were lucky enough to, so we have several chains. We can change the exciton-photon detuning, so we can change the gain. And we were lucky enough to be able to choose an exciton-photon detuning, which allows the gap, the lasing, to be triggered on the edge state. So this is what you see above threshold, so 1.5 times the power at threshold. And you see that the mode is, the emission is really completely dominated by the emission of this gap state. Okay, this is what we, okay. So, this is, sorry, I was looking fast. So this is the emission pattern that we observe. So here there is absolutely no spatial resolution, no spectral resolution. You see that most of the emission really comes from this edge state with this PY orientation. So then the question is, are we just looking at lasing, a regular lasing on a topological state, or can we say that it's a topological laser, which means that it has some robustness, which is different from what we would obtain from lasing on just a regular localized mode. So we try to think about the symmetry of this Hamiltonian and what we can deduce about the robustness. So if we look at this time-bending Hamiltonian, we see that it commutes with sigma z, so the Pauli matrices, which has just 1 and minus 1 on the diagonal. So since there is a 0 on the diagonal, we commute with this operator. So this is what is called the chiral symmetry. So it is because we have 2 sublattices. So this is the same as in graphene. And so you have actually particular properties coming from this chiral symmetry. The fact that the spectrum of eigenstate is symmetric around 0, and that you expect to have edge states at an energy E equals 0. And so what you see is that if you introduce fluctuation in T and T prime, but you do not modify the 0 on the diagonal, you will not affect this commutation, and so you will preserve this symmetry. So it means that if you introduce fluctuation on T and T prime, disorder on T and T prime, you will not modify the energy of your edge state and its localization. So we did not do that experimentally, but we show you here a simulation where we introduce fluctuation in the relative amplitude of T and T prime. And when alpha is equal to 1, it means that the amplitude corresponds to the hopping energy between two sides. So what you see is that it's produced a mess in the bulk band, but the topological state remains nicely resolved at an energy which is 0. And here you see the probability density of the topological mode on the first pillar, and you see that it stays equal to 1 quite long. I mean, the system, so the localization and the energy of this edge state is extremely robust to fluctuation. Okay? So now, how the state, so what happens when we break this chiral symmetry, which means we change the energy on the diagonal. So the most severe way of doing that is just to blue shift the first pillar. So to change the energy of the first pillar, this is where the localized state sits. So it's really modifying a lot the potential landscape in the region where the edge state is feeling a lot, this perturbation. You see that if I change the energy of a pillar which sits here, it's not going to affect a lot this edge state. So what you see that indeed you break this chiral symmetry, so the energy is not robust. You don't have a zero energy mode anymore. And so what you see is that this is the energy of the edge state, so the topological state, as a function of the perturbation, so the potential you introduce on the first pillar. So what you see is that it actually traverses the gap. It is blue shifted and eventually merge into the bulk states of the upper P band. So what you see is that the localization of the mode, when you do that, so the probability density on the first pillar is actually quite robust as long as you stay quite far away from the gap. So you stay highly localized until you eventually get completely delocalized when you hybridize with the bulk mode. So there is some reminiscence of the topological robustness regarding the localization. So the states will remain localized as long as you are sufficiently deep in the gap. So to do that, I could ask you, how do I do that? It's very easy. I just pump one pillar, and I've explained you in great detail last time that when we pump, we create an excitonic reservoir, and the excitonic reservoir creates a blue shift. So that's what we want. When we pump the first pillar, we get eventually phasing on the edge states, but this is quite normal because we essentially pump very efficiently this edge state. And so we can look at the localization of this edge state, see how it evolves. So what you see, for example, here at 1.5 PTH, you see that the gap has been really shifted a lot. It's almost in the upper band. And still, this is the image we get. You see that it's still highly localized on the first pillar. Okay, so this is the experimental measurement superposed to the calculation. And you see that we have actually a very high localization. So the state is still quite immune to the blue shift of the first pillar as long as it's not too big. So we have some topological properties which are preserved. So we dare to say that maybe this is a topological laser. What is strange in our experiment is that we don't see the delocalization. Here there is no time reversal symmetry. We don't break time reversal symmetry. We are just playing, it's really a toy model where we are just playing with this symmetry, which comes from the fact that we have A and B sides. That's all. We are not exactly. That's all. So maybe it's not, but I'm not the only one to call it a chiral symmetry. I did not invent the word, but probably there is the same word which is used for two different things. So here it's just a property to commute with symmetry, which is to have the same on-site energy in this system. Okay? Probably much more simple than the chiral symmetry that you are addressing. So it's really a toy model. We are just beginners trying to enter. Okay, so where am I? So just, where am I? So, as you know, in this structure, we have both topological chain, the one for the py orbitals, but we have also a trivial chain, which is for the px orbitals. Okay, so it's just looking at the other subset. So when we consider this chain and we don't introduce this change in energy of the first pillar, we have no edge state. But then when we blue shift the first pillar, this is as if we were creating a defect in a periodic chain. You actually create also an edge state, which is a time state, which is well known. Okay? So we have also actually two time states which are formed in the p orbitals, which so they do not exist for zero perturbation, and they emerge as you increase the on-site energy of the first pillar. Okay, and they go into the gap. Actually, if you really increase a lot U1, so you completely detune the first pillar with respect to the others, it's as if you were removing one pillar from the chain, and then actually one of these time states is going to become topological, because this is the px orbital, which is going to be topological, and the py trivial, because you have removed one pillar. Okay, so we have always the coexistence of these time states and these topological states. So what you see in the calculation is that contrary to the topological states, which localization is very strong only on the first pillar and independent on this perturbation that we introduce, the time states, they do not exist, so they are just delocalized in the band for zero perturbation, and then their localization, so this is the localization on the first pillar, so you see that they are essentially localized on the second and third pillar, and their localization changes a lot with the perturbation. So these kind of states, which origin is not coming from topology, their shape changes a lot, and so as a function of perturbation, and so these states are really trivial from the topological point of view. Okay, so these states, we can see them in the experiment and see that indeed their localization changes a lot. Okay, but one of these time states is going to progressively localize only on the second pillar. When I remove completely the first pillar, this one is going to become the topological state eventually. Okay? So the conclusion is that when we look at this end state, its existence is determined by topology, so by the bulk edge correspondence. It's really related to the bulk characteristic, and its localization is quite robust to local perturbation, even if you start to break chiral symmetry. And this is very different from the time edge states, which are trivial from the topological point of view, which localization is governed by the perturbation you introduce, and which localization changes a lot with the perturbation. Okay, so it's just considered as a milestone to be able to lace on a topological state, but of course this is a 0D state, it cannot propagate, it's a bit trivial, and so this is just the first step. What is very interesting now is really to move to 2D sample and try to be able to lace, for example, on 1D edge states and see eventually if non-linearity can be interesting. Yes? So what we do is where are they? So here, what we have is you talk about that, for example? So here, what we do is we image the structure with quite a big magnitude on the entrance slit of our spectrometer. And so what we measure is for a given position, so defined by the slit, emission as a function of y along the wire in vertical, so the wire is like this, and we make a cut with our slit and look as a function of position on the wire and energy for a given x. Then we move the length and we do the same for a different x. So at the end, we get a matrix, a big matrix, with intensity as a function of energy, x and y. And then we make a cut in this matrix at a given energy, and this is how we get these images. Okay? So here, for example, this is for a given slit, the image we get. So this is directly an image for a given position as a function of energy and position. So this picture that you get when you look that way, this is directly what we see on higher than Px. There are both Py and Px here. It's the same. We don't choose actually. The only way to choose is to have one lace. So this is the only way where we can see really. So we choose, sorry. Here, where is lost? So you see that the only way we can really distinguish Py from Px is in the first pillar, because here in the gap there is only Py, and here there is only Px. But otherwise we cannot. We just change the gain so that the gain is, so actually what you see is that when, so there are plenty, so when we make this experiment, so the gain is in this region. And here there are a lot of modes, so there is a lot of competition. Whereas here there is just a very peak density of states, and this is why this mode laces first. When we just put our excitation spot in the bulk, so we don't overlap with the edge states, and we look at lasing, we see a lot of mode competition in the big base. So this mode, which has a very peak density of states, takes the gain. So it's the one that we meant by the group of Moti-Segev. They use coupled waveguides, and so they study the propagation of light in this waveguide, and actually the Z coordinate is playing the role of time. So they look at the evolution along Z of the system, and this is a way, an analog way of looking at the time dependence of the system. And so the fact that they look like, I don't know how you say tire-bouchon in English, and I'm not sure we should talk about it. It's going to remind, sorry? Voilà. So this actually implement a floqué Hamiltonian, and that way you can get a nice topological edge state. So here what we want to do is to try to etch a honeycomb lattice of micropillars. So it's much more complicated than just engineering 1D lattice, because you have to dig quite big hole, small and big holes. So this is more complicated, and the optical quality of this 2D lattice is not as good as the 1D. So we are trying to work on the technology. But this is enough for the moment to, for example, resolve the band structure of our polariton. So here what you see is different sets of bands. The first one comes from the hybridization of the lowest energy states of each pillar, so the S band, and this gives really the physics of graphy. And then we have higher order modes, which come from hybridization of Px and Py. And there is also very interesting physics to be done here, and this physics is more difficult to explore in different systems. And there is a flat band. Yes. Sorry? A cat face. So here I should put a dot, and then it's true. I never saw, and the G's are here. Okay. I see that you are very concentrated. Jacqueline cat face. Is it dead or alive, this cat? Is it a Schrödinger? Maybe. Okay, so what you see here directly are the Dirac cones. Okay, so this is a cut again. This is so here we are imaging Kx and Ky. Okay, so here on the entrance slit of our spectrometer, we image the Fourier plane of the collection length. So we have Kx and Ky. We choose a given Kx, and so vertically we have Ky, and horizontally we have energy. Okay, so this image, if you look like it like this, it doesn't look like a cat, but it looks like what we have directly on the screen of the CCD camera. Okay, and then if you make a cut, so when we monitor this kind of image, we record them for different value of Kx. So we have a big matrix with intensity as a function of energy, Kx and Ky. We can make a cut at the energy corresponding to the Dirac cones, and we see nicely the 4 Dirac points, okay, and the first mini-Brillouin zone, and so on. So we can really explore completely the states in real and reciprocal space. what we can also do is engineer the edges and look at edge states. So actually in this artificial graphene, there are 4 kinds of edges. So like in real graphene, we can engineer zigzag edges or armchair edges. And there is another one which does not exist because where you have free bonding. So this cannot exist in real graphene because the atoms will rearrange to minimize their energy, but our poor pillar, they cannot move. They have to stay like this. So it's possible to engineer this so-called birded edge. Okay? And so we can look at these different edges, both in real and reciprocal space, and study edge states. Okay? Sorry? So there is no scale. So typically the lattice parameter is of the order of 2 microns. So I don't know how many, this must be like 200 microns. Like 200. So what the calculation tells us is that, of course, you all know that there are no edge states for the s orbital for armchair edges, and there are edge states in zigzag edges, but also there are edge states for birded edge. Okay? So I'm not going to show you all the images. If you are interested, this is the detail is explained in this paper. I will just show you one example of this kind of measurements. So where you see at the edge of a zigzag edge, you see in reciprocal space and in real space, so signature of the edge states where we expect them to be. So for the moment, unfortunately, the Q factor is really degraded by this etching process. So we have not yet been able to observe propagation of the edge states because the lifetime is too short. So we are still quite limited by the technology, the kind of experiments we can do, except just looking at their spectroscopy. But still, there are very interesting things to study when you look at the orbital states, so the p states. So actually, you have new edge states. So here in red, so these are the calculations where you see that you expect also zero energy mode, but also dispersive edge states that we see in the experiment. And we are working very hard with Gilles Montambo, Jacopo Carusoto, and Tomoki Ozawa to understand the topological origin of this. So if they have topological properties, actually there are also very interesting things that you can observe in the p-band when you put a strain. So to mimic a strain, you just have to change the distance progressively along one direction. Then you distort your band structure. There is actually a topological phase transition that occurs in the p-band. So there is really new physics to explore, just doing linear spectroscopy of these p-bands in a honeycomb lattice. I'm not going to enter into detail of that. I just want to spend the last minutes talking about the future. So how can we progress? Well, how can we really build a topological photonic insulator? So to do that, we need both a Zeeman splitting and a spin-orbit coupling. So how do you understand that? So if you zoom at the dispersion of polariton close to a Dirac point, so we have a degeneracy, it's sigma plus and sigma minus, so we have a double degeneracy. And so what we need is first to have a Zeeman splitting to lift the degeneracy between sigma plus and sigma minus. And then what you see is that you have some crossing between sigma plus and sigma minus. And if you are able to introduce spin-orbit coupling, then you end up with a band structure which looks like this, and which is necessary for this photonic topological insulator. So polarization, the pseudo-spin of the polariton. So what we want is polariton to be able to travel just in one direction. And what you will see so what you want is, for example, sigma. So the only way to do that and to break time reversal symmetry is to address the spin degree of freedom and to have, for example, sigma plus polariton traveling that way. And the only way they can be backscattered is if they are if the spin is splitted. So if it's scattered to sigma minus, which is very difficult to do, so there is going to be a topological protection for light polarized along sigma plus. to be able to have no backscattering, we need to have edge states, edge mode, which are sigma plus and sigma minus, and not linearly polarized. So the way to do that is to really engineer. So how can we get a Zeeman splitting? It's because excitons have a Zeeman splitting. So we are going to use the matter part of Polariton to induce a Zeeman splitting. And then the spin-orbit coupling is given for free in our structure. I don't know if I will have time to describe that, but we have it. So there has been a proposal which was done by two different groups, which is to put a honeycomb lattice, or a Polariton system, in a magnetic field to get Zeeman splitting and make use of this spin-orbit coupling to actually engineer edge states. So you see that here in red you have just the states that are on the right side of the lattice, and you see that actually there are only sigma plus polaritons which we propagate on one plane. Okay, so this is a dream. So we are actually now engineering the structure to have the largest Zeeman splitting as possible, because the size of the gap is actually related to the Zeeman splitting. So if we want to be able to have nicely resolved edge states inside the gap, we need the gap to be large enough. And then we need also to engineer the spin-orbit coupling. So I don't know, what is this time? Does it include the question or not? Including the question, because it says 4 minutes. We are delayed? Yeah, but I'm not sure this guy is delayed. Okay. I'm not sure you are still able to. So I plan to explain how we demonstrated that there was spin-orbit coupling in the elementary building block of the graphene, which is the benzene molecule. I'm not sure I'm going to go into that. If you are interested, there is a paper. It's too specialized. So anyway, I'm just going to show you that we demonstrated that actually, so the states are in such a benzene molecule, they have both an angular momentum and the polarization degree of freedom, and we could show that there are states like this, which are a linear superposition of angular momentum -1 sigma plus, angular momentum +1 sigma minus. So there is a mixing between orbital degree of freedom and polarization, which is the spin-orbit coupling. And we could demonstrate that. So looking at, for example, sigma plus, we could show that indeed the phase is then rotating. So there is a pi rotation, which is corresponding to L equal to, for example, -1. And if we look at sigma minus, we have an angular momentum which is opposite. So we have indeed the eigenstates of such a photonic molecule have a fine structure which is related to the spin-orbit. If you are interested, you go to the publication and they can answer your question. So then if we manage to put all this together, so have a strong TETM splitting in a honeycomb lattice plus magnetic field, we should be able to have, so this is a simulation, but we would like to see that. So this is a sigma plus, for example, edge state. In the simulation, they introduced a disorder here. There is a missing pillar, and the edge state doesn't care and goes straight. Okay, so this would be really an achievement to do that. We are not there yet. So then, for the perspective, in lattices, I just explained you how we can observe lasing, but then we can also use non-linearity. So in our system, there is a very strong Kerr non-linearity. So this Kerr non-linearity is responsible for optical stability, which has been observed in planar samples in the group of Elisabeth Jacobino quite a long time ago. And then you can start to play with stability and coherent drive in more complex systems. So we have recently done an experiment on 2 coupled pillars. So this is really the simplest lattice as possible. And so pumping just one of them, we observed stability. And we observed actually a hopping phase between the 2 pillars, which is driven by interaction, and self-trapping of light. So there are already quite a lot of interesting nonlinear things to do there. Then we did also dynamical hysteresis, so looking at the time at which you sweep the hysteresis, the power, and seeing actually the effect of quantum fluctuation on the hysteresis area. And this was even done just on one pillar. So if you put all this and you start to play with non-linearity in a lattice, and you can engineer the way you pump the system, maybe introduce some feedback, I think this is a playground that we have not finished exploring. Then what about the quantum regime? I'm sure one of you will ask, so I answer before I get the question. So I give you numbers. So the Polariton interaction, which I call J here. So I'm answering questions, so I still discuss. Typically, what we measure for the blue shift induced by interaction, this is the number we tend now to agree more. So if the order of a few microeV micron square, which means that if I take a pillar which has an area of 1 micron, the blue shift, so the U that I will get, the on-site interaction I will get, is of the order of 1 to a few microeV, which means that if I want to be able to get the polariton blockade, so have a single polariton nonlinearity larger than the line width, which is what is necessary, I need a Q larger than 1 million for a pillar of 1 micron square. And we are maybe close to that number, but for a pillar with an area which is 10 times larger. And when we start to reduce the size, in our system, gamma increases dramatically. So we have really to work to try to get there. In the most optimistic evaluation of U over gamma, we are more around 0.1. And so we need to gain a factor of. So maybe these open cavities, where they say that they are able to make really a small cavity, maybe this is the best way to try to get into this U over this polariton blockade regime. So then there are these proposals that Ashish described this morning. I don't know if they are interesting or not, at least for us they are new. So they looked interesting, but maybe they are not so new. But this is this idea of unconventional polariton blockade, so which was initially proposed when pumping such a system with 2 coupled cavities, the idea that you could see anti-bunching in the light emitted by the driven pillar. So I know that there are many people trying to do that. This is already a very difficult experiment for us. If it's not interesting, I don't know, we have to discuss. Maybe looking at lattices with this excitation scheme could be interesting. So this is still to discuss. So with this, before finishing, I would like to thank all the people with whom I got the chance to work along the years. So as you can imagine, we absolutely need our theoretician collaborators. So we have been collaborating with quite many different people depending on the different subject we were addressing. So when we talk about the reservoir and the condensation, how it works, we interact a lot with the group in Clermont-Ferrand in France from Guillaume Malcuèche and Dimitri Sonnichkov. We work a lot also with Christian Luciuti and his young colleagues when addressing for example, dynamical hysteresis. We work a lot with Jacopo and Tomoki Ozawa, both on the instability problem, also with Michiel Wouters and Daniele De Bernardis, and also on the graphene. They are very interested in these p orbitals. Eric Ackermann really inspired us a lot for the Fibonacci experiments. We also worked with Hakan Turecci, Sebastian Schmidt, DJ, and Matteo Biondi on the flat band physics, which I did not address here. And Gilles Montambeau is really interested in the topological properties of our p orbitals and if there are topological phase transition to be seen and to be explored in our system. And then, of course, there is our experimental group, which was first at LPN and now at C2N. So here, this was a nice opportunity to gather everybody. So, of course, I have to really acknowledge Alberto Amo, who joined the group in 2011, and we did really fantastic collaboration. Unfortunately, for personal reasons, which are fortunate, but not fortunate for me, he's going to move very soon to build a new group in Lille, but we really want to continue working together on Polaritons. And then, so I want to acknowledge all the young people, PhD and postdocs, who have been working with us along the years. Also, as you have seen, samples is really a crucial ingredient in everything we do. So we are extremely grateful for the epitaxy to Aristide Lemaitre and his colleague Carmen Gomez and other colleagues over the years. And Isabelle Sagne is the magic person who was able to develop this etching process that actually we are the only one to be able to master. So even if we destroy everything, even if we remove the quantum wells everywhere, we still have quite nice optical properties which allow us to do everything. And with this, I would like to thank you for your attention. And I survived these 3 lectures. I'm very happy. You have enough.
Maybe not question.
Sorry?
I had a small. So I realize it's quasi-crystal model is kind of slightly different from quantum Hall because quantum Hall effect we need to break time-also symmetry. Here we don't need to have such a thing. Probably this is because phase is not this phase on phase is not an explicit like variable. We can sweeping it.
Exactly. So the way we sweep phi is probably, and the direction in which we sweep phi is probably a way to break time reversal symmetry in this synthetic dimension. It's really toy model.
Yeah, I really like it. All the authors I know because at that time I was a postdoc in Weizmann and all of them are the last year PhD student. At that time, it's a lot of fun discussing topological physics. Yeah.
Okay. Thank you.
Let's thank Jacqueline again.